So I have the last lot of the day, which means I'm standing between you and the beer. So I have to make sure that I'm here on time. So if need be, I'll cut some corners. You cannot see anything yet. My original talk title is like really big. It doesn't even fit on the screen. And something about JDK 9 and upgrade, etc. But actually, the new title is called Performance After 8, because I'm going to tell you about performance in Java after release 8. Because I think for most of us here in the audience, just a quick poll, who's running Java 8 in production? Like 90% of you. Java 7? Okay, couple of hands. Who is brave enough to have Java 9 in production? Okay, sort of one hand, but nobody uses that. Okay, there is a reason for that. So the talk will answer some questions, why it is that way, and I'll tell you what's going on now in Java after release 9. Who am I? I'm one of the disorganizers for 2 unconferences. One is JCrete on the island of Crete, another one is JAlba, which is going to happen in Scotland. We start in May this year. This will be awesome. I work for Canoe, one of the sponsors of this event. So let's move on. The agenda of the talk is I'm going to talk about release cadence of Java, then a couple of interesting JEPs in JDK 9 and new APIs, and then we conclude with some parting thoughts, what it all means for you. Okay, Java release cadence. I don't know how many of you have seen something like that. And that is the new reality. Prior to Java 9, we lived in the world where every new release of Java would cook for some years, usually 2 to 3. Some releases were much longer. But then basically we have this huge Java release, and then we can move on. Well, starting with JDK 10, Java will release every 6 months. So you see, Java 9 was released just September last year. It's going to be end of life in 2 weeks. Then we have Java 10 for 6 months. It's going to be also end of life. And then from there on, we'll have a long-term support release, Java 11. So, okay, what's the difference? And what do I mean by end of life? Of course, the code will still be there. This release will not have updates anymore. So in the older versions of Java, every new major release, like when Java 8 was released, it end of life Java 7, which was kind of okay, because it was already time to move on to something new. Now, with Java 10 release, which is 6 months after Java 9 release, what do I do with Java 9? Well, this is a problem. So essentially, if you're not a paying customer, you have to kind of think for yourself, do I use the new features of new release? Or do I stay for long-term support releases, which Oracle will support for 3 years? So like Java 11, which comes September this year, will be supported for 3 years until 2021. And at which point the Java 17 will be released. So you can just jump from Java 11 to Java 17, which is pretty scary. And you're missing like 5 releases in between. Or you go to another vendor, and down there I have a link for the blog post by Simon Ritter from Azul, where they explain how they're gonna handle the situation. And for instance, Azul, with their Zulu OpenJDK build, will offer 1 year support for the intermediate releases, so Java 9 will be supported until Java 10 essentially is over by the Oracle release and so on, and much longer supports for the long-term support releases. Okay, so this is a new model. So new releases come in every 6 months. I think for us Java developers, it's a big news and big shift, but if you look at the other communities like Go, they also release a bunch of times a year, and everybody's jumping to new release without any problem, so we'll have to adjust to that. All right, so let's start digging into the performance, or like what we mean by performance, what kind of speed benefits and other cool, exciting things we have in JDK 9. And of course, I couldn't miss a big elephant in the room, which is modules. What do I mean by modules? I'm not talking about like defining modules and working with modules. I want to take on the premise of how the module thing started. So it started with Project Jigsaw as an attempt to modularize and take apart the JDK itself. And one of the premises was, because you can like break apart big monolith JDK, you can have a smaller footprint and put Java on the smaller devices. etc., etc., etc. And of course, as having a smaller thing, smaller footprint, we got the premise of faster startups, because Java startup, JVM startup sucks. So this thing supposed to help us. And here just list of all the JEPs and JP Java enhancement proposals which went into JDK 9 all related to modules. There's the whole zoo of different things, starting from modularizing the JDK itself down to cool things like JLinker. So you have a linker now in Java. Welcome C++. I've never seen, was a long time ago. And we can ahead of time compile it in Java. Okay, so let me just look at one dimension on JDK 9. So I decided to compare, because JDK 9 is so modular and so small, what is the footprint of the JDK 9 releases? And here's a table just showing you JDK 8 and GRE 8 compared to JDK 9 and GRE 9. And as you see, on essentially both dimensions, both download size and the installed size, it sucks. It's actually bigger than the JDK 8, so even though we have modules, well, we have to pay cost for it. Okay, so, well, this is not the most exciting thing. Let's move on. So meet my friend, Hello World app. You've seen that. And let's just run it and time what it takes, the start, essentially the execution time of the program. So you're starting an app both in JDK 8 and JDK 9. And as you see, I'm using perf, I'm doing like 50 repetitions, I'm doing something scientific, and all of a sudden I see, okay, Java 9 sucks. Just by using old ClassPass and jar options, I'm losing. I mean, come on. But then I thought to myself, well, I know the answer. The answer is obviously modules, right? So I build myself a module, and I run with the modules. And like, oh man, okay, what does it all mean? All right, so I have some other options besides that. One of the premise was exactly the JLinker. What JLinker allows you to do, it allows you to build out of your app a native application, so to speak. So it packages the bits of GRE, the modules of GRE that you use in the modules of your app and your dependencies into one package. So I decided, okay, let's build that thing, which is called Hello App in this case. Which is, by the way, has an awesome footprint. Just building this Hello World app, it's 45 megs on the disk, unlike almost 600 megabytes for the JDK itself. So I have really nice thing, and I can just use Java minus module, and I don't have to specify ClassPass because it's built into that image. So JLinker build me an image. Okay, I'm building that, and I'm down to essentially ClassPass option. So yay, I can still use modules and be on par with the ClassPass option with JDK 9, but I'm not close to the JDK 8 startup. All right, let's use heavy machinery. I know. One of the things was ahead of time compilation. Come on, we go native, right? Even the web technologists mention native. Everybody goes native. So we go native. So what you see by these two commands highlighted here, I built two things. I ahead of time compile my module, which is called Hello SO in this case. And I compiled Hello SO and the Java base module. So if I run just with mine, man, it sucks even more than without ahead of time compilation. If I run it with Java base, it's a disaster. And the reason why, because the Java base, as far as I understand, when you specify the IoT library, it memory maps the files. So it reads, goes through them. Compiling Java base takes a long time, several minutes if I'm not mistaken. It throws megabytes of exceptions, but that's okay. Everybody say it's okay. It's supposed to be like that. There are some issues with ahead of time compilation, and it produces a binary which is like 300 megabytes or something like that. I mean, it's really ridiculous. Okay, so in this case, there is one more feature I haven't tried, and it's called class data sharing. Who heard of this feature? Okay, some people, like, I see three hands in the room. This is available since Java 5. So what you can do with this feature, and I show you the final result, you see this, let me see if I can point to that now, whatever. This X-share on option. So I'm using the class data sharing option and running JDK 9, and all of a sudden we managed to beat JDK 8, like, almost. We're on par with JDK 8 and ClassPass option. Right, but this is not fair comparison because I'm enabling class data sharing on JDK 9, but this is features in Java 5. So let's enable it in JDK 8. game over. So at this time, I say, okay, one day we will have better, faster systems, startup times with Java. It's just not today. Which brings us to the next topics, and I'm here. I will cover briefly first two JEPs. Not going to cover them in depth because they're just important to mention. First one is the Java level compiler interface. This is the thing that enables the Holy Grail. Who've been to the GURL VM talk today? I see a couple of hands. This thing enables to run GURL on the JVM. So essentially, this allows to hook into the VM and replace the hotspot C2 compiler with the compiler written by Java. In this case, it's GURL. Just a couple of things to mention. This incubating feature enabled in JDK 9. In JDK 10, there is JEPs 317, which is essentially enabling the GURL compiler. This is just enabling the entry point to the compiler where you have to build compiler yourself and plug it in. In JDK 10, you can just enable with two command line flags, you enable the GURL compiler, and you can actually test your application against GURL, which will be embedded with the JDK installation, which is awesome. And second thing, the GURL is used to ahead of time compile. So ahead of time compilation is actually based on GURL. And the third thing, Twitter is using it as we speak in production. And there's a guy called Chris Tellinger from the VM team at Twitter. He has a talk where he explains why they switched their custom OpenJDK build to use GURL and how they benefit with their Scala code base using that. Another sort of a big elephant in the room, and the offender in terms of performance measurements, is a G1 compiler. For better or for worse, guys at Oracle decided they don't want to support all the GC combinations out there, and they decided that we should all switch to one and only true GC, which is in this case is G1, and they made a default collector. So what are the problems with that? Well, the problem is default changed. If you were serious about garbage collection, you monitored it and tuned it, most likely you define your algorithm and you'd specify GC explicitly. So it will not affect you if you run it on default. Here be dragons. If you want to use G1 and you're serious about that and want to switch and try G1, you need the JDK 10. Because JDK 10 brings a first time parallel full stop GC to G1. Prior to JDK 10, full GC, like GC of the full heap, will stop the world, is single-threaded. So with JDK 10, at least the worst poses will be much smaller. And here be dragons. Here's a blog post link, what a difference VM make, by Nitsan Vakar, the guy who created JC tools, where he recently investigated the problem why his log-free data structures running super cool on JDK 8, suck on JDK 9, and it boils down basically to the default GC. Switching on JDK 9 to parallel GC fixes the problem, and the culprit there is that GC, for its own bookkeeping, inserts some instructions to the code, like card marking, and that thing all of a sudden puts a lock. So you have a log-free data structure which has locks in it, inserted by the runtime. Awesome, isn't it? So that's why we've seen on the previous slides as well, and for all my measurements, I always use it parallel GC on the JDK 9. So I'm comparing apples and apples. I'm running the same garbage collector in both cases. And by the way, JDK 9 also deprecates CMS collector. So moving forward around JDK 10, essentially you have like two parallel GC and G1. And there are some exciting garbage collection technologies coming. One is Zero GC, ZGC, it's called by Oracle, for huge heaps, and another one is Shenandoah from Red Hat. But nobody gives us timeline when they will arrive, so keep an eye on the space. So let's move on to really exciting things. One of the biggest changes in the JDK 9 release in terms of performance was compact strings. So what compact strings are is, let me show you an example first. Compact strings, let me rewind. What you see on the screen is a little program which has a string value, lorem ipsum, blah, blah, blah. You can Google and Wikipedia find the full text for it. Redacted, it's a long thing. And I am printing the class layout and the graph and the footprint of an instance. And I run this program both on JDK 9 and JDK 8. So if you run it on JDK 8, we see what our string class is. So our string class has essentially two fields. Well, it's an object header followed by a value, which is character array, and a hash code, a hash for the hash code. And it's 24 bytes. So empty string, just by sheer class overhead, is 24 bytes. So if you put one character in a string, it cannot be less than 24 bytes. In fact, it will be much more. But this is 24 bytes. And down there below, you see the footprint of this of my test text that I put there, and it's 936 bytes. Okay. So what we see in JDK 8 is that every character or every element of the string, every character of the string is a character in Java terms. This is 2 bytes, which is 2 bytes because Java uses UTF-16 encoding. Okay. What guys at Oracle did, they analyzed a bunch of heap dumps and realized that up to 25 to 30% of all the heaps are taken by strings. And most of those strings are ASCII or Latin 1 encoded, which means the essentially character is 1 byte, but we are paying for 2 bytes for that thing. So they said, okay, what can we do about it? So they came up with the idea to replace our character array value, which is highlighted here, with a byte array. And we see other thing here, which is a new field called coder, that you can decide what it is. Is it Latin 1 encoding or is it UTF-16? Instance, like a string instance size, still 24 bytes, nothing changed, but look at the footprint size difference. So we had 1936 bytes before, 488. So in total it's almost twice 2x, but if you compare the two arrays, like character array and the byte array content-wise, you will realize that it's exactly 2x reduction in the memory footprint. All right, so if we switch to JDK 9, we get by default compact strings, and if our compact strings are, if the strings that we're using is Latin 1 encoded, we're using less heap, so we can utilize it better. We put less garbage collection pressure, everything is okay. But what it means in terms of performance in terms of basic operations, because string is not just a storage of characters we do something with. We iterate over characters, we do substring on it, we to lowercase it, to make a case insensitive map lookups, etc., etc., etc. So I decided to create a couple of benchmarks. One is called the basic one, just in this case measures 4 operations, like walking the character array, using to lowercase, and doing substring at the beginning and the end. I will just explain why with my test data. And here are the results. So what I'm doing, I'm having 2 strings which character-wise have the same length. So it's 16 characters. One string is Latin 1 encoded, another string is UTF-16. And as you see, iteration time is a bit better in JDK 9, but I would say it essentially didn't change. And this was one of the biggest concerns of the performance team at Oracle, that you cannot regress the string. So if you make changes to something fundamental as string in the JDK, you better be sure that performance will stay on par. And then you see something like stop string head having the same, more or less the same speed, allocates the same amount of bytes, everything is awesome. You see substring tail has an interesting story here for when the string is UTF-16 encoded. So in JDK 8, it's 13 milliseconds, or not, milliseconds, nanoseconds for this operation. And in JDK 9, it's 18.8 nanoseconds. And actually, JDK 9 in this case allocates even more bytes. So what happens here is that you have a string which is UTF-16 encoded, but if you split it into sizes, into pieces, it could be that the piece that you take out could be compressed now to Latin 1. So what they do, they opportunistically, every time you take a piece out of a bigger UTF-16 string, trying to compress it. So in this case, they allocate a storage array 12 bytes, going compressing it, and upon second character realizing that this character is not Latin 1 encoded, so you have to throw away array and start again by allocating bigger byte array and putting stuff unencoded there. So that's why we see some small regression in here. So I think it's a reasonable price to pay, especially if you look into other potential gains, like for example, to lowercase. Example, if you see Latin 1 encoded string in JDK 8 and Latin 1 encoded string in JDK 9, It's like 1.8x in performance improvement and more than 2.5 times footprint improvement on a string. So essentially, the smaller your string, smaller your storage, less bytes you allocate, less pressure you put on the allocate and garbage collector, you get performance benefits. All right, but that's not all string does, right? String does some other funky operations, like you search string with index of, you have the searching starts with, ends with, and you have things like equals and compare to, is quite heavily used. So let's look at those operations. This is quite packed screen, so no worries. It's just like the full combination of, now I have two values. So I have the same strings, and just full combination between parameters. So Latin 1 versus UTF-16, Latin 1 versus Latin 1, etc. So you have like four values per operation. And so far the story, it's more or less the same. Okay, I highlighted a couple of things here. Down there at the equals, you see that JDK 9 is much faster. And for two particular cases, and the cases are when the strings have different encoding. Because if strings have different encoding, their byte coder is different. There is no reason to compare content. So the JDK 9 has an implementation optimization saying if coder is different, screw this, equals false. Because they cannot be equal by definition. If the encoding is the same, of course, you have to perform the full encoding thing. And a similar stuff, of course, exists for things like index of. Because if I'm having a Latin 1 string and I'm searching something that is UTF-16 encoding, I know for sure this string cannot contain that. So again, 7.7 nanoseconds for the second row there for JDK 8 and 2.4 for JDK 9 because say it's a no-op. There is nothing for me to do. Okay, there is there are always pros and cons of doing something, right? The same goes here. Here's a thing called string max size. So what we see here is that this is a little tiny program that runs nice on JDK 8, provided you have enough heap. Well, you need 8 gig. Everything's fine. And in JDK 9, you see this bizarre error. Out of memory error, UTF-16 string size. Well, essentially what it tells us is that the byte array storage that we have in a string cannot hold more than 1.something billion entries, whereas the character this is basically the byte array, right? And whereas the character array before was able to hold essentially twice more characters in this case. And the problem only appears if you have UTF-16 encoding, because for UTF-16, for every entry in your array, you need 2 slots. So before it was 1 slot, no problem. Now you all of a sudden need, you basically double your storage capacity. So, and this is the price to pay. So the guys at Oracle say, well, if your problem is strings with billions of characters, you probably have some other problems. And funny thing enough, if I run it, if I don't put these funny characters there and I keep it Latin 1 encoded, it works. Because the compression algorithm kicks in and it figures out that it can compress the whole character array directly to one-to-one to byte array, and then there is no exception. Another interesting feature added to JDK 9, also related to strings, is called indefined string concatenation. Quick show of hands, who knows what this code at the bottom compiles to on pretty much any release of Java starting Java 5? I guess shout out what it does? String builder, yes. So how everybody used to think about it, whenever you have the string concatenation pieces which you don't explicitly manage, like language one, this is a syntactic sugar essentially that the Java C provides you to generate a string builder behind the scenes and do it like this. So let's have this example and look at Java P disassembly in JDK 8. It's a huge roll of text, but what you have to follow the comments on the right hand side from you, and you see basically we are allocating a string builder, we add in a left square bracket to it, then we call current time millis, and essentially this whole dance with the string builder stuff. Okay, what's the problem with that? The problem is simple. Because this is a sugar that is spit out by the Java C, Once your program is compiled, it will stay the same for as long as your jar or your class file lives. And this means it precludes JVM from optimizing string concatenation. It's essentially like, it's there, there's nothing to do. So what the guys, again, performance team at Oracle decided to do, they decided to change it. And they decided to use a funky technique called Invoke Dynamic. So GSR 292, back in Java 7 was added for, essentially for the implementing dynamic languages. And since then, this horse is used for lots of different things, including lambdas and stuff. So how it looks in JDK 9. So all of a sudden, our method compiled to essentially 6 instructions, or 7 bytecodes essentially calls. In this case, we just acquire current time millis, and the important bit is this one highlighted instruction, invoke dynamic call. And this invoke dynamic call, strangely enough, has just 3 parameters, which is capital J stays for long, then comes our Java lang string, and then an integer. So it's a 3-argument method call, very strange, it returns a string. And then afterwards, we put the string into the print line, which is essentially a system out call. And down at the bottom, I'm showing you what's the invoke dynamic. I don't know how many of you have heard about invoke dynamic. It's essentially a 2-stage process. When you invoke dynamic bytecode, by the way, normally the Java C is not emitting that bytecode. This is JDK 9 for string concatenation. There is no way to do it from Java. You have to write like through ASM or bytebody, whatever. You can put this instruction. But essentially two-stage process. While normal invokes like invoke special, invoke static, etc. in Java knows what you're calling. It knows the target. With invoke dynamic, the target is unknown. So the process is 2-stage. First, there is a bootstrap method call. So you call somebody to tell you what are you calling to establish that thing, and that's like a linking step. And afterwards, all subsequent calls from their own call directly that method. So here, down at the bottom, we see the bootstrap method definition, which in this case points to something interesting called Java lang invoke string concat factory, make concat with constants, and highlighted in blue down there, it gives this strange argument. This argument is a string. It's called a recipe for building the concatenation with constants, as the name implies. And as you see by the shape, this is our string from the example. We have bracket, spaces, parentheses, and this U001 is a placeholder for the parameters. So first parameter is our long, which is current time millis, the first argument to our method. Second one is a message, and the third one is a count. So it exactly mimics the thing. So in essence, what it does, essentially, it built a recipe. It realized that there are constants in this recipe. So it compiles down, it generates a method handle, which accepts 3 parameters, because everything else, our constants, are built behind the scenes and plugged into the story. Okay, so they did this funny thing, very, very cool. Doesn't matter. Well, let's look at if it works, clicky. Okay, let's look at the benchmark. I'm essentially logging the same message that's shown on the previous slide, running it with GMH, and then you see these numbers. So concatenating with JDK 8 compared to JDK 9, so essentially we have like 3x in performance, and we are more than 3x in footprint. And if you look closely at this 80-byte operations a second, and if you look closely at the data, it's essentially the exact size of the string that we are concatenating. There is not a single byte wasted. Down from the second row down, I'm running on the JDK 9 with different options. One is, I thought, okay, maybe it's compact strings, Who knows, the combination of the two, of course, is the best. Let's run without compact strings, just with optimized concat, and we still essentially have the same performance. Of course, we lose some bytes in the process, which is expected because strings are now bigger, but who cares? And the rest of the experiment is essentially inside the string concat factory. If you look inside it, it defines 6 strategies for doing actual concatenation. There is one default for the second row not shown here, and there are 5 explicit ones shown here. Essentially, they split into two categories. One is bytecode generation, which is all strategies prefixed with BC underscore, and then method handle base. And these first five, essentially, all of them essentially delegate at the end to the string builder. And the different combinations of size and size exact is how they precise the storage. So they just say, okay, if I know all the arguments and I put all the sizes together and I can create a string builder with the proper size, it doesn't have to resize internally. So it's just a game of how the thing. But okay, but what makes the default so fast? Well, the default is called MH inline sized exact. What it means is that instead of using a string builder API, they allocate in a byte array and write into the byte array directly. And the coolest thing of all, if you look at how it is done, because it's a method handle based, there is no code generation. It's essentially kind of like generating code on the fly. During the first bootstrap call, the method handle will be created. Method handle is creating kind of like a subtree, like a node of trees, like IR if you like, or abstract syntax tree if you're familiar with parsers. It builds that recipe and gives you the method handle, and from now on you call in that, and essentially you generated code on the fly. And I was like, before looking at this example, I was not aware that you can use essentially method handles for code generation without code generating and without resorting to the bytecode management, which is super cool. And of course, there is always a caveat, and the caveat is this: if you think, okay, the concatenation is so awesome, I'm going to stop using string builders and going to use just default concat. Yes, as long as you don't use loops. As long as you have loops like that, where the warning suggests result plus equals is actually mandating that the new string will be allocated. This is in JLS. So you cannot avoid allocation of a new strings. It will be allocated and discarded, allocated and discarded. So if you don't believe me, let's run the benchmark and let's see the times. If you're on JDK 8, you see a huge difference. It's like 5x in performance. In JDK 9, everything is better because JDK 9 is smarter with the storage and the concatenations and allocations. You still pay like almost 2x for it. But look at the memory. Even if you're on JDK 9, you're paying 5x more in the garbage generated. And of course, that means pressure to garbage collector, means more pauses, means slowdown. All right, those were our strings. What else we have in store? We have lots of stuff in JDK 9. One of the interesting ones are convenience factory methods for collections. I think most of you heard about them. They look something like this. Now you can create a list, or rather not just a list, but a mutable list by calling list of from 0 to 10 arguments, and then comes another overload with like var args array, so it's unlimited. The same goes for set, and for map up to 10 key value pairs, you have an off method, and if you have more than 10, then you have to use off entries. Okay, new collections, what's the big deal? Syntactic sugar, you know, before you say arrays as list, that's it. Well, they're immutable, so you have to put like immutable collection around it or whatever. Okay, well, not just that. These collections are first and foremost optimized also for storage. So unlike the generic collections, these collections promise that they like keep overhead to minimum and provide the super cool new functionality like being immutable. So let's just have a quick look. This is a slide with a list. And what you see here and different incarnations of the list interspersed with list of. So I'm basically comparing one-to-one what it means to create an empty list with the new functionality, old functionality, 1 element, 2 elements, 10 elements. And as you see, first two rows are not interesting because list of and empty list are constants. Nothing to see here. List of 1 and the singleton list from collections, the same. And you see I'm storing a 16-bit or rather 16-byte object, which is in this case integer, and the overhead is like 60%. So okay, I'm not winning anything. Let's create an array list, and all of a sudden array list is like 64 bytes because array list inside itself contains an array which must be allocated. An array is an object which has a header 12 bytes plus 4 bytes length, so it adds at least 16 bytes on top of it, plus you put a value inside. It means another 4 bytes, which is already 20, and object alignment rules tell us that it must be at least 24. So here you see how we go from 40 to 64. We got 24 bytes of overhead. Linked list, even worse. It creates the linked list node with the pointers to it, 72 bytes, and you see the overhead is just increasing. And it's basically the same story goes if we continue adding more elements to our list. And at 10 elements, okay, one thing to note here, the list and set have specialized cases for empty 1 and 2 elements. That's why I'm showing empty 1, 2, and then more than that. So as you see, for instance, list of 2 is 56 bytes, only 43% of overhead, and already array list and linked list suck big time, so we just add the thing. But once we go over 3, like starting from 3 elements on, list of and new array list is essentially the same. They have the same overhead because it's implemented in exactly the same way. The list of more than 3 elements onwards has an array inside it. Okay, this is kind of okay. We gain something on par with array list, much nicer syntax. Let's move on. Let's take a set. I guess set is like a real deal thing here. Again, empty one's not interesting. Set of 1 element, collection singleton have us covered here. Well, let's create a hash set with 1 entry in it. Boom, 208 bytes. So it's like 90% overheads. Like, don't even bother. Link hash set, even more. 3 set. Better story there. Just for those who don't remember, all the hash sets, 3 sets, link hash sets, etc. in Java implemented on top of hash maps. So a hash set is essentially containing a field of hash map and storing everything in the map. So you're essentially paying for the costs of the map. And the trend continues. The more data you put, basically the more overhead you see. And it's especially bad with lead hash map. There are maps. Just shown here for completeness. I'm not gonna spend too much time on it, but just look at the last 4 rows. What I did on top of just adding like sequential elements from 1 to 10 to the map, I decided to create a hash map collision. When a hash map collision is when all your entries have the same hash code, which essentially provoke anomalic behaviors in the hash map. Prior to Java 8, the hash map would degrade to a linked list data structure inside it. With Java 8 onwards, it builds a binary tree. So what I'm doing here, essentially, I'm creating the collisions and seeing what's the overhead of what becomes of our collection if the collisions are present. And you see my data size is quite substantial. It's like half a K. And the map of entries essentially has fixed overhead. It's quite easy because map of entries is just an array. While the hash map, link hash map, and the tree map all have much more overhead. These things like hash map has now inside a table, like an array of buckets plus a tree towards it, and it's just ridiculous, the overheads. So as we see, the first thing is the collections they deliver on promise and bring the memory down. So let's look at some numbers. So this is just some picks from the benchmarks I did. List contains in the list. Depends what kind of list. There is a list of, array list, and linked list. Quite simple. 1 and 2 element special cases and list of win across the board. Very easy. And go into 10 elements, list of an array list essentially behave the same. And same for 100 elements because they are the same. There is an array inside. And linked list, as you see, walk-in linked list, essentially it's a pointer chasing, it's a cache misses, and it's just the performance drains down the drain. Essentially, if you are take something out of the stock, don't use linked list at all in your code. There is no reason for it. There are some special cases which might call of them if you like add at the beginning and do frequent removals, but on the normal code, never do that. Similar stuff for set. It says list of, but it's actually set of because everything else is hash set and link hash set here. Quite interesting for special cases of 1 and 2 elements. It's way faster, like 2x faster than everything else. And then it gets funky because then we don't have the performance advantage anymore. Even though we have this specialized storage, we have an array inside that thing, it doesn't work this way. And this is quite easy to explain. The reason is they decided to put a feature into the set of and map of implementations, which is called randomize traversal order. I don't know if you've been bitten by the bugs before that like iteration order of the hash map is never specified. So if you have tree map is one thing because it's sorted, but the hash map is like random. And there was a change between Java 7 and Java 8, I think, broke lots of programs. And they decided to avoid this thing in the future by saying, okay, sets and maps obtained through the factory methods will randomize the order once per VM start. So once you start a VM, the order would be randomly chosen, and then it uses some funky while loop by essentially jumping to different places. Or like, for instance, the 2-element thing. Once you call the iteration, you have 1 and 2 element. Second time you get another iterate, and they get 2 and 1. So they flip as they see fit the order. So you cannot rely on the order of the thing. And it seems like these things have exactly the negative performance impact on those. Okay, let me move on. I have about 10 minutes. I'm near the end of the thing. So stack walking. I don't know if you know about that, but back in old Java days, sometimes you needed to inspect the stack or like know who is the caller of the method is. So there was a way to use reflection, sunMISC reflection.getCaller, which is proprietary API, which is no longer possible in Java 9. And essentially that class is deprecated, still kind of you can get it to work, but nonetheless in JDK 9 you have a new API to do the job. But let's look first, what would you do in Java 8? In Java 8, and the way to get a stack trace is essentially create an exception asking for stack trace, or go into thread.get stack trace, which essentially creates exception for you if it's for single thread, or if you have all stack traces of the application, then you can say thread get all stack traces. So that's the old way to do it, and the new way is to use new API called StackWalker. You obtain an instance of it. There are several methods to get it with and without parameters. I'm using the special one here to be able to use get caller feature. Otherwise, it's not available. But nonetheless, it's essentially you see for getting caller, it's a single method, get caller. For walking the stack, you have a single method, walk, which receives a stream of thing called stack frame, which is a new interface, and you are walking that stream, which means you're not in control of the stream. Whoever gave you the stream can close it upon you. So it's a very clever design. They could have just said, call a method, get a stream, and do whatever you like with the stream, but then you are, the client, the caller, is responsible for the stream. And with inverting that and saying the stream will be parameter to your function, you have to give a lambda or a function in order to process the stream. They're in control of the stream. So in other words, they can close the stream, for example, because stream is holding to the current thread's stack information. So if they would give you as a stream, by the time you leave in the call, the thread stack trace changed. So it mutated. So it just doesn't work. So by having you, basically, they giving you just this one little window, when they give you the stream, they're in control and saying, okay, this is now a stable view of the stack. You doing the call. By the time call finished, the stack is gone. Well, this view of the stack is gone, so you cannot harm them, and they can give you some cool things. So here I'm just doing like a count of the stream and just walk the whole thing. And for the getting top 10 frames, I'm just limiting the stream to top 10 and collecting to a list. I mean, nothing special here. Standard Java 8. Okay, so let's see what. I mean, that doesn't matter. So if you look at the exceptions, what you see, the pattern is quite simple. The deeper is your stack size, like in one case is 10 frames, in another case 100 frames, more time you pay. And the time now is not in nanoseconds, it's in microseconds. So it doesn't matter which operation I'm doing, it costs the same. Because every time you have to get the full stack trace, you have to get the array with the stack trace, they all materialized, you get that, and then you move on from there. And if you use a new API, caller class is essentially constant time operation. It doesn't depend on the stack depth, essentially. Stack depth is quite funny, because for stack depth, I have to walk the whole stack and call a count at the end. And when walking the stack is lazy. So the stacked frames that this API is giving you have to be created on the fly. So as you see, as the size increases from 10 to 100, so does the time. So it's more than 4 times slower, because that's the deeper the stack. And getting the top 10 frames, essentially constant, because it's always top 10 frames, and it's just the price for these 10 frames to get. All right. One more topic on my agenda. This is not a JEP. This is what the new APIs in the JDK Everything found with add since 9. There is lots of stuff. Couple of things highlighted here have to do with performance. First one is fuse multiply add. There is an instruction in the modern CPUs to do that. It's more for correctness, not for performance. I actually did a benchmark and I didn't see performance benefit, but you get better rounding results. But two other groups are quite interesting. One is different check index, helper APIs. Come on, just checking, if index less than, greater than, whatever, some simple stuff. But what is important, those things are heavily inlined and intrinsified, and actually almost all JDK is now using those. Instead of putting in explicit checks or writing them own ifs or whatever, by using this essentially an entry methods on the objects, the hotspot knows, this is a special thing, I know how to optimize that. So it has a special code. It recognizes the code shape by seeing the call into these methods, and they're used. And another thing is there's a bunch of stuff added to arrays. You see like new compare methods, compare unsigned, equals methods with lots of funny, like you can have an equals on the portion of the array. And the last two ones, as I actually are the building blocks for the rest, is called array mismatch. So given two arrays, you can find an index at which arrays diverge. If the arrays are equal, there is no such index, or you find the first index, the divergence of the array. So let's have a quick look how that might look like. Naive approach and the one that we use in library. So naive approach is basically you're walking both arrays simultaneously, obviously to the length of the smallest array. So you stop at that. And if the length was the same and you didn't find anything, it's like, okay, there is no such index, otherwise you return the index. All right, so doesn't matter. Let's run it. Oh, yes, it does. It does big time. So it's like the bigger your array, once you're crossing the threshold of like 100 or 1,000 elements, you essentially see more than 10x performance, 10 towards 15x performance difference. And the reason is being the arrays mismatch is operating on the strides of 8 bytes. So if I'm walking here byte by byte, they can get a chunk of memory and analyze that. By the way, this feature is used heavily already in Apache Lucene, together with object check index. They also use in the multi-release jar of JDK 9 to be able to benefit from the feature. So once you start using your solo Lucene instances on a JDK 9, you should get even more benefit by not just strings but also these things. Okay, let's quickly recap. Java changed release model, releases every 6 months. Releases not created equal. Some releases are long-term support, some releases not. So you have to think what it means and how do you sell the upgrade to your boss. Before it was easy. It's the biggest new thing. Old version is end of life. We get new security patches, etc. I think it's harder this time. JDK 9 has lots of stuff. I didn't cover lots of different things. There is a lot of changes to concurrency. Like on-spin wait hint, like optimized locking, etc., etc. So it's just tons of stuff. Encryption also, improvements to encryption. JDK 10 is bringing more stuff. The GURL is coming closer, so we can experiment then with JDK 10 using GURL instead of C2 and see if our Java apps or our polyglot apps, Groovy apps, whatever, will benefit from that. And some improvements to G1 and some other stuff. Bunch of references and questions, if you might. Of course, there's a beer in like 1 minute. So if anybody has a question or remark or comment. Okay, no questions. It seems like beer o'clock. There is one question. Okay, it's really, I cannot see half of the audience because of the lights, so sorry for that.
Thank you very, very much for your nice presentation. I'm interested whether we should really be concerned about startup times. You showed performance of a Hello World, and is it really that bad with a real world application?
I would probably say no. I kind of anticipated this question. The question is the startup time. Doesn't matter. I mean, if you launch in something like your Spring Boot app or your JBoss and it takes 3 minutes to kick that off, difference in between 20 or 50 milliseconds or even 150 milliseconds will make no difference. You will not see that. This is more for stuff like, microservices or restarting something or something smaller. They using Java in for different deeds, like maybe doing some little scripting in Java and writing apps and invoking Java to do that. That's where it matters. But it was more an exercise to see, did it deliver on promise? Modular Java should have better footprint, have better startup, and it didn't, at least in my test. Actually, I found a blog post by some other guy who did almost the same steps, and he went even further to selectively ahead of time compile. You can compile module directly, or you can give it a list of methods that you need. So he went all the way there, dumping all the methods that his hello world or whatever his app was doing needed, and compile only that, and even managed to get some millisecond improvements. But it's ridiculous the amount of pain you have to go to get there. I think what you get already, you get linker, so you can build your application into a releasable package, which you don't need to install Java, and you have all the modules together there. I think that's already super beneficial. And if it takes 20 milliseconds longer to start than JDK8, who cares? In JDK8, you didn't have that. You had to build your Docker container and put JDK there, whatever. Now you can essentially using Java tools already have your application in a runnable state and deliverable state. And it actually can create an exe. When you build a JLinker, you can provide an exe, so you have an executable to run the application.
Yes, thank you. And one remark about the string overhead. I'm assuming you measured with the 32 mode JVM, 32-bit mode.
No, I'm using the compressed OOPS. I'm running with default. This is, I'm not sure. I think I didn't put it down, unfortunately. I'm printing the VM details, but it's essentially default mode on 64-bit VM. Plus, with JDK 9 doesn't have 32-bit VM.
Okay.
He said goodbye. That's another thing. If you are having some 32-bit platforms and you're planning to upgrade to a new JDK, since JDK 9 there is no 32-bit releases by Oracle. There might be ARM ports 32-bit, but Windows, Linux, and it's gone. So there is no 32-bit. Java has moved on.
So it's improved because previously the overhead was 42 bytes for a 64-bit VM.
It uses compressed OOPS. So the default mode, if your heap size is is below 32 gigabytes, VM is able to compress the pointers from 8 bytes to 4 bytes. So that's where you get the benefit from. And that's, of course, in fact, alignments on all the sizes, yes.
Okay, so not a question, but just a remark on the startup times. We had a very different experience with JDK 9. It's actually, when you start complex application, for example, for us is Jetty, it's actually 4 or 5 times faster starting in JDK 9 than JDK 8. And this is due to way improved class loading. When JDK 9 starts up, it has all the metadata about classes, where they are, how to load them into memory, etc. Rather, in JDK 8, you had to crack open the jars, scan all the jar. Maybe the cluster you need to load is the last one in the list of entries in that jar. So it takes way more time. So for complex application, I think JDK 9 is way faster. It was actually the first time that I tried to start Jetty with JDK 9. I was actually surprised because it was I was used to wait up to 30 seconds to start up. And then with JDK 9 it was 2 seconds and it started. And I said, there's something wrong. And then I checked everything and everything was starting just fine. So no, I would like to counter your argument. It's probably true for the hello world, but the more classes you load, probably, the way better is JDK 9.
That's true. I didn't make the test. Thanks for the remark. I think is very important. So it's even more encouraging. So encouraging people to upgrade. But I guess all of us are waiting for LTS 11 release. I don't think I think it's a safe bet to assume that you can start playing with 10, but it's gonna be gone in 6 months. Or there's another way: you start upgrading every 6 months. You just say, okay, now with Java, I'm going to upgrade my Java release every 6 months. And if you're in control of it, if you ship your app with JLink or whatever, or Docker images, you can do that. All right. Thank you very much for coming. And the beer time.